Thank you. Thank you for introduction. I will start my presentation. That is just talking about a very, very strange story on materials. And in the field of chemistry or catalysis or engineering, we use materials, especially we like solid material, like the catalyst or photocatalyst. And we use the term, the design of materials, the synthesis, fabrication of materials, and characterization or quality control of materials. Yes, and probably you have some publication using those terms in title. And of course, I have some or many papers, including those terms, design, synthesis, fabrication of something. But this might be illusion unless identified. It is possible to say that is illusion, at least in the field of organic chemistry. So in the field of organic chemistry, identification is essential. This, for example, the Journal of Organic Chemistry published by American Chemical Society requested the authors identification by at least elemental analysis data within 0.3% error. That is very, very severe restriction. 0.3% error. If you have experience of organic synthesis, the elemental analysis data within 0.3% error is very, very tough, challenging. And the nuclear magnetic resonance spectrum, this shows the skeleton. That is how the carbon atoms are interconnected. And by using those data, it is possible to identify. This is a very famous toxic compound extracted from sea animal. And once this is reported as an article in the field of organic chemistry, the author extracted this from sea animal. Yes, and once this is identified. And then the very famous Professor Kishi totally synthesized this compound and report. And of course, at that time, that is identified. What is the meaning of identification of this organic compound? That is to put the precise IUPAC name. IUPAC is the International Union of Pure and Applied Chemistry. So important point is this name is unique. Unique means this name strictly shows this molecular structure. Yes. So in the field of organic chemistry, the meaning of identification is to put a name reflecting the precise molecular structure. So this is the meaning of identification. So it is necessary to put a name. And in the field of inorganic or material sciences, for example, titania is often used as a catalyst, a photocatalyst, or the other kind of materials. Yes. And what is the name? Titanium 4 oxide. And this just tells the composition, the ratio of number of atoms, Ti and O2 to be 122. And sometimes we measure the XRD, X-ray diffraction, to determine the crystalline structure into, for example, the anatase rutile brookite. This is the name of crystalline of titanium oxide. But we know, even if the same anatase or rutile or brookite structure, still those material is at least a bit different. So there is some difference, even if that crystalline structure is determined. In the IUPAC recommendation of inorganic compound, they say, in general, it is very difficult to give the systematic name reflecting the structure is very difficult. So therefore, we are waived to identify inorganic compounds. That we should remind that why in the field of organic chemistry, the identification is necessary. So that means in previously, someone might report without identification or with misidentification. There's so much trouble happen. So therefore, they make this rule to identify any organic compound. So then in the field of inorganic chemistry or material science, there must be the trouble without identification. So we need to identify that. As IUPAC recommendation said, that it is so much difficult to determine the structure because at least the solid material has bulk structure. And probably you think it is not so difficult because the XRD shows the crystalline structure as a bulk structure. But that is based on the neglection of amorphous phase. And we neglect the presence and how much amount of amorphous phases are there. We neglect it. And solid material, of course, has surfaces that is completely different from bulk. And there is not, it is a bit difficult or rather difficult to describe the surface structure. And of course, there is some distribution of different type of surface structure. So that is so much difficult. And even if we can determine the bulk and the surface structure, still we need to determine the size. And of course, you know that the size has some distribution, not uniform. So therefore, it is a bit difficult to describe, not a bit, very, very difficult to describe the structure of solid materials. So then, what we can measure as a structural property is crystalline structure, primary particle size, secondary particle size, and specific surface area. Well, probably no other conventional comprehensive method for analysis of solid structure. Probably you know him, and probably you know him in front of you. Yes. Do you think these two guys are identical? Probably you say no. That I think those two guys are identical because the thin hair, wireframe glasses, gray beard and mustache, and the ring on left third finger, and the black turtleneck, etc., and handsome. So 6 parameters are the same. For solid material, only we measure the 4 parameters, and this is 6 parameters, and the 6 parameters are the same. So we should think those two guys are identical. But probably you don't think so. If you see the fingerprint of those two guys are identical, you should believe those two guys are identical. And if the fingerprint is different with each other, you can say those two guys are not identical. So fingerprint is important. When I was a graduate student, every chemical laboratory, not limited to organic chemistry, in organic chemistry, the other kind of chemistry, our laboratory has infrared spectrometer. And there is a region of fingerprint region between 650 wave number to 1,300 wave number. Those region is called the fingerprint region. And this is the salicylic acid. So if you prepare the sample and that compound show the fingerprint region, same as this, you can say that is salicylic acid. So at that time, and even now, not all the peaks and the intensity, peak position and the intensity are not interpreted precisely. So even if we don't know the meaning, why these peak appears in this region, you can use as a fingerprint. So that is the meaning of fingerprint. So if we can obtain the fingerprint for those inorganic solid compounds, it is possible to identify inorganic solids. And now I want to propose that ERDT CBB pattern can be used as a fingerprint of solid inorganic materials. And without using the other conventional analytical data, I think it is possible to identify organic solid compounds by using ERDT CBB pattern. And what is ERDT CBB pattern? ERDT is energy reserved distribution of electron traps, and CBB is a conduction band bottom. And those combined pattern can be used as a fingerprint for identification of inorganic compounds, such as metal oxide powders. How can we obtain ERDT CBB? This is the schematic diagram that we use the two beams. One light beam is used to excite valence band electron directly into electron trap. Here, the meaning of electron trap is just the vacant electronic state. We don't know what is the precise structure, but just the structure accepting electron, that is the vacant electronic state. And once those electronic states, electron trap accept the electron, the new photoabsorption appears. So for example, titanium, if that is reduced, the blue color or blue-gray color happens. So that is new absorption. And the second beam is used to detect this new photoabsorption by photoacoustic spectroscopy. So this is the newly developed reverse double beam photoacoustic spectroscopy. And this is a real setup. The sample folder is almost the same as XRD. And the powder sample, thin film sample, and the bulk sample can be measured. And the left top one, that is the photoacoustic signal by scanning the excitation light from longer wavelength side to shorter wavelength side. And here, the new absorption appears, and that is increasing. And this is accumulation of electron traps, electron in electron traps. And then that is differentiated to give energy reserved distribution of electron traps in relative scale. And this relative scale amount is converted into absolute value by comparing with the chemical titration method. Using the same setup, we can measure the photoabsorption like PA spectrum. So by the interpolation of this linear line, we can determine the photoabsorption edge wavelengths. And this can be used as a band gap data. And the electron trap distribution, ERDT, is plotted against valence band top position because the electron in valence band is excited to electron traps. So from the band gap energy data, it is possible to show the CBB position as a line in the same scale. And this is the commercial titanium oxide samples. And this has the specific surface area 52 and annotates with small amount router. But without using this data, and 152, this is the total density. And by using this ERDT pattern, only this titanium oxide can be identified. And this is a representative commercial titanium oxide samples. And A annotates R router and B brookite. And the ERDT CBB pattern is really different depending on the bulk crystalline structure. But even amorphous titania shows such a pattern, a bit different, the higher energy position, but it is possible to say, even if the bulk structure is completely amorphous, it is possible to obtain such ERDT pattern. And the important point is the total density of electron trap is almost linearly increased with specific surface area. This tells that electron traps are located mainly on the surface, and that is not something like a point defect. That might be on the surface reconstruction structure. And the estimated density is about 1 electron trap per square nanometer. And therefore, the annotated samples with, for example, TiO13 and the TiO1 that has almost the same specific surface area, but the pattern is completely different. So therefore, the ERDT pattern, such a pattern, reflects the surface structure. So this is only the part of commercial sample results, titanium oxide samples, and you can see those patterns are completely different with each other, and that can be used as a fingerprint. And why this can be used as a fingerprint? That is the minimum requisite of identification of a solid compound is bulk structure, bulk surface size, and the surface structure. And the ERDT CBB pattern contains all of those structural parameters. ERDT pattern reflects the surface structure. CBB reflects the bulk structure, and total density reflects the size, because the TD is almost linearly increased with specific surface area. So then another kind of metal oxide can be, and this is the results of the titanium nanotube prepared by anodization of titanium, metallic titanium plate. And for the thicker samples, it is possible to obtain such a pattern, and they are different with each other depending on the preparation condition. This is the first example of showing such a difference depending on the preparation conditions. And the even amorphous sample can be measured. This is a niobium oxide, and this gray part is completely amorphous, no XRD peaks. But the ERDT pattern is almost the same as a crystalline samples. And titanium thin film can be measured. So this is from private company in Japan. And depending on the preparation conditions and the post-treatment, the surface structure is completely different. And probably this is the only one possible analytical method for such a thin film of titanium oxide. And even insulators, if that is doped or with impurities, it is possible to see such a pattern. And I think that almost all the metal oxide can be measured by using this technique. Also, carbon nitride, that is an inorganic semiconductor. And it is possible to prepare by using different type of precursors, that the product is almost the same in XRD pattern, even if the different kind of precursor is used. And by checking the ERDT CPV pattern, it is clear that the oxygen-containing precursor gives the lower energy peaks, and the sulfur-containing precursor more positive, more lower energy peaks. And this is due to the surface doping with those heteroatoms, oxygen or nitrogen. And to check the similarity or identicalness of patterns, we introduced a new parameter, that is zeta. Zeta is the multiplication of 3 partial degree of coincidence. One is the ERDT CBV pattern, the shape, matching of shape. And the second one is zeta D, that is the total density. And zeta C is a conduction band of photon position. Each degree of coincidence, partial degree of coincidence, is calculated to give between the value between 1 and 0. 1 is completely the same, 0 is completely different. And checking the commercial titanium sample, and the sampling is carefully taken from the almost the same position in the same bottle. And you can see the very, very similar patterns. And calculating a zeta value, that is almost 0.9. So therefore, it is possible to say if the degree of coincidence is almost 0.9, those pairs of samples are almost identical. And important point is, if the sample is taken a bit different position even in the same bottle, the pattern is a bit different. And the zeta value is decreased from 0.9 to 0.7 or 0.8. So the 2 points. One is this technique is very, very sensitive, especially for surface structure. And the second point is such a powder sample in the bottle, even if the same bottle in the same package in the same code name, there is some heterogeneity in the structure. And this is the power of results of pairs of titanium oxide, commercial titanium oxide samples. And almost all the combination pairs show the very low zeta value. Of course, this is natural because they are different titanium oxides, so therefore zeta value is low. But several pairs show the high degree of coincidence. This is the top 7 rank of higher degree of coincidence sample pairs. And the rank 2, TiO4 and P25, rank 3, TiO8 and ST01, and TiO11 with FP6, they show the high degree of coincidence, but they are almost, that is the same product that supplied from the same company that is provided in different way with different code name. So this is the natural. However, even if this is the ranks 2 one, that is zeta value 0.76, lower than 0.8. And remember that the same sample gives 0.9. So therefore, even if the same code name or same product, the different lot of production or different storage condition may give some difference. And the important point is this column is the degree of coincidence of photocatalytic activity. This is the average of 3 photocatalytic reactions. So that means if the activity is the same, that is 1. And the higher degree of coincidence pairs gives the higher degree of photocatalytic activity coincidence. To make it clear, the zeta PC, degree of coincidence of photocatalytic activity, is plotted against the zeta value. And there is almost no relation. But here is a line. So high degree of coincidence pairs don't give the low degree of coincidence of photocatalytic activity. That is, similar sample gives similar photocatalytic activity. And by taking the moving average, the zeta value below 0.6, that is so much scattered. So accidentally, the same photocatalytic activity or accidentally low degree coincidence of photocatalytic activity. However, if the zeta value is higher than 0.6, the zeta PC is increasing to give almost 1 at the zeta equal 0.8. Yes, so that means the similar photocatalysis, titanium oxide gives similar photocatalytic activity. And we love this elephant plot. And this is first published in Chemical Communication in 2016. And this is open access, and you can download this freely. And important point is if the same ERDT CBB pattern is obtained, the pair must show the same property, activity, performance, everything. So because they are identical. And if the property, activity, performance, those properties are different, the ERDT CBB pattern must be different. So this is the important point. But even if the same property or activity, so that doesn't guarantee the same ERDT CBB pattern. Different ERDT CBB pattern doesn't guarantee the different property, and accidentally same or accidentally different. So we check the ERDT CBB pattern for those photocatalytic reactions: hydrogen production, carbon dioxide production, and oxygen evolution reactions. And the ERDT CBB pattern is arranged in the order of photocatalytic activity. So the left top is the highest, the 100 relative activity, and the decreasing, and decreasing, and this is the worst. And that for hydrogen evolution case, the worst one has 6%, and CO2 10%, and O2 1%. And there is almost no similarity in the neighborhood, but for carbon dioxide and oxygen case, if the relative activity is higher than 70 or 69, the pattern is similar. But middle or low activity sample doesn't give any similarity in the neighborhood. So that is important. So those photocatalysts are well balanced in several structural parameters, but those middle or low activity sample is inactive with different reasons. Sometimes, for example, the specific surface area problem, or sometimes the defect problem, or the other kind of. So the reason or low activity is different depending on this. So that for hydrogen case, that is in situ platinum deposition is included. So therefore, two-step reaction, and it is a bit not completely well balanced. So that means it is possible to expect the higher photocatalytic sample by controlling the reaction conditions. And Tolstoy said in the novel, a very, very famous novel, Anna Karenina, the happy families are all alike. Every unhappy family is unhappy in its own way. And I'd like to say, active photocatalyst powders are all alike. Every inactive powder is inactive in its own way. Yes. So just 2 days before, our review paper is accepted in Catalysis Science and Technology. You can freely download this one. And we are very much happy to accept any samples from you. And we have so many collaborations with universities or institution or private company in the world. And I'm very happy to accept your samples. And please make contact if you are interested in. So I will put this email address in the chat box in this conference. Thank you very much for your kind attention.
Thank you, Dr. Ohtani. Thanks for your time and presentation. Is there any questions from the audience?
Yes, I would like to, I have a question. So first, yeah, I'm Natasha Novak-Tushar. I'm coming from Slovenia, from the National Institute of Chemistry. And
Hi.
Professor, yeah, hello, Professor Ohtani, thank you very much for really very nice and interesting talk. And actually, I have a question concerning the instrument. So
yes.
Now this technique as an instrument is available only at your laboratory, or you already contact some companies and that will be commercialized, or?
Yes, we are now collaborating with a private company in Japan to commercialize this instrument. But at present, no such a commercial product. And we have 5 setup, laboratory made 5 set. And almost all the instruments are working every day and almost every time, and we accepting. So probably during the course, but probably within 1 or 1.5 years, the commercialized will be achieved.
Okay, so how broad you go in the powders? For example, I have some zeolites, so that means aluminosilicates doped with metals. For example, a zeolite, which is aluminosilicate doped with nickel. So if I have 2 such products and they are working in different way, but I see by ERDT that they should work the same, can I send them to you for this characterization?
Yes. So I think the silica or alumina or zeolite, those insulator has a very large band gap, and in our instrument, the limitation of wavelength of irradiation light that doesn't give any peak for those large band gap materials. However, something is introduced in the framework or on the surface that might give new absorption, new electron traps, and that can be. And what I can say every time accepting those questions, that is try it. So just try. And there is, of course, no guarantee that your sample gives the good ERDT pattern, but try it. So there is a chance, yes.
But the samples has to be photocatalyst.
No, nothing. Not limited. So any, at least I can say that any metal oxide with the band gap below smaller than 4 electron volt, that is every time gives the good ERDT CBB pattern.
Okay, thank you very much. And
thank
again,
you.
Very nice
and
talk.
We are waiting for your sample. Yeah.
Okay, thank you.
Yes. Is there any other question from the audience? Yes. If not, we can go ahead with the next presentation.
Dr. Bunsho.
Yes.
For the valuable presentation.
It's not a question, doctor. He is just congratulating Dr. Osman.
Do you have any question?
You don't have any question. He is just congratulating you, Dr. Osman.
Thanks very much, Dr. Bunsho,
yes,
for the valuable presentation.
Thank you.
Yeah, fine.